So recording is on. I'm not going to put on the chat because this time of the year, not many people are using the chat. In case you have a question, just speak up. I'm not putting on the chat because it does occupy part of my screen then, and also have to pay attention to that separately. It's easier for me just to listen. If you have a question, to speak up. So where were we last week? In my opinion, the most direct application of a normally hyperbolic invariant manifold theory is geometric singular perturbation theory. It's an ongoing research area, still very active, and a number of problems fit in this framework. So that's what I was finishing up the discussion on. Remember that singular perturbation, broadly speaking, is the study of systems with several different time scales. What we can have as a rigorous treatment for such systems, the only one I'm aware of, I mean, there are a little bit of extensions of this, but the only one I'm aware of where you can make this fully rigorous is systems with two different time scales. So such systems you can split into a set of slow variables, n-dimensional, and a set of fast variables, m-dimensional. And the fast and slowness is apparent from the presence of the small parameter, which multiplies the fast variables. And they're fast because if you put this on the other side, then it becomes a 1 over epsilon. And you see then y dot varies a whole lot faster than x dot, right? You can think of a soft, stiff partition in a mechanical system or something like that. Generally speaking, higher modes in any physical oscillatory system tend to be stiffer. So at least heuristically, you might think of a threshold between the two, and whatever is below that threshold is slowly varying. Whatever is beyond that threshold is fast varying. That's precisely the challenge, by the way, to establish this global splitting of variables in a real life system is hard, okay? Because it's more of a soft splitting, right? You imagine you have lots of modes, and where do you draw the line, right? Because you could say, does it really matter? It does, because when you set epsilon equal to 0, you will designate some modes to work with versus other modes, right? So it does separate, does introduce a separation, but in some systems that's more transparent than in others. Okay, so what can you do? Well, we went through this machinery of locating critical manifolds in the rescaled system, and this was Fenichel's idea, and then how those perturb into slow manifolds. And then I also talked about the fibration of the stable manifold, of the slow manifold, when it's an attracting manifold, and basically a way of determining where particular initial conditions go. And the fibers are, for epsilon small, are close to these vertical hyperplanes. And therefore, for small perturbations, you can sort of guess where things go. So one important area of application is inertial particle motion. Inertial particles are finite-sized particles. Their motion departs from the infinitesimal particle motion that you would have in any fluid. And in particular, there was perhaps this was the first analysis that I have seen for this, in which geometric singular perturbation theory was applied to this setting of initial particles. Actually, that might not be true, but at least at this level of generality. And the story is about von Karman vortex shedding behind a bluff body. And the observation is that even though you normally have this vortex street here, and that's what you would see when you put dye in there, so you're tracking the fluid particle motion. When you put in finite-sized particles, there tends to be focusing. And by focusing, people mean that there would have to be a quick convergence to a wavy center line in this wake. So instead of the particles, doing this or that, or just traveling, that there seems to be an accumulation, a dissipative effect. And this paper is a nice explanation for that. And the beauty of it, I think, partly is that it does it under the weakest assumption. So it doesn't assume too much. it does assume, which helps, that the flow is steady in a co-moving frame, co-moving with the vortices. That's why you just have a two-dimensional steady velocity field. It does assume that the flow is two-dimensional. Epsilon characterizes the size of the particles after non-dimensionalization. The initial particle velocity is y, but it's equal to x dot. So x is the position of the initial particle, not the fluid particle. And once you have simplified the Maxey-Riley equation to the extent you can, you basically just keep the Stokes drag. Then the equation becomes incredibly simple. Again, this is just F equals ma. Epsilon is like a mass type term. This is acceleration. And the main force that remains after you removed all those beautiful, hard to figure out effects is the Stokes drag, which basically tells you that you're being damped. There's a resistant force, which is the negative of your relative velocity to the fluid. So it would be minus v minus u, right? Because v is your particle velocity relative to the fluid is v minus u. So you would have an opposing force minus v minus u. So that becomes u minus v when you work out that sign. So this is the basic equation of motion, kind of the simplest equation that can capture this phenomenon. And because the particle is small, this is a classic example of a slow-fast system. So that is that natural partition right there. When it's two-dimensional motion, the next is two-dimensional, but the equation also works in three dimensions. So either you have a four-dimensional system or you have a six-dimensional system. And we looked at the analysis of the system for epsilon equals 0. Remember, you introduced the fast time like that. And this was your f, and this is your g. The variable x1, remember, that was actually taken to be periodic in this case, even though in real life it isn't. But for a finite piece of the wake, with a good approximation, you can consider the vortex street to be periodic. And that's what the periodicity of the x1 reflects. X2, the other direction, is not periodic. So that's just a transverse direction. Okay, so when you go through the machinery and you set epsilon equal to 0, you get the simplest possible critical manifold in this problem. Remember how to identify the critical manifold. You look for fixed points in this equation. You can do that with ease because in this limit, x is just a parameter that doesn't change. So it's frozen. So you can freeze that parameter here and solve this equation as a function of x. And for that, because of the construct, you will get typically manifolds of fixed points because x is a parameter that you can freely choose. And for any value of that x, you find the y, and this then gives you this critical manifold. The critical manifold is also particularly simple. It's a graph. Immediately, you don't have to work expressing y as a function of x. It's given to you in that form already. In our previous notation, it's phi naught of x. And what it is basically the velocity field itself. Okay, so this is what the fluid velocity field viewed as a graph, interestingly, is your critical manifold. Its stability check. Remember, this is an important thing, and this is largely the difference between the heuristic approach that is still followed by some, but certainly was prevalent before Fenichel came up with this. And I went through that. I'm not going to repeat that, but one way or another, people would arrive at this conclusion because, you know, their usual argument would be is that why don't we set epsilon equal to 0 and view this as a constraint and solve it as a constraint. The constraint says y equals u of x, and plug that into the equation here, and you're done. So the basic difference between this approach and that approach is that that approach, as I said, sometimes actually gives reasonable results when you simulate it. Sometimes it doesn't. So when it doesn't because the critical manifold is unstable. So you will not see that as an attracting state. There is therefore this important step of checking the stability of M naught for two reasons. That is it relevant as an asymptotic target, and A, is it normally hyperbolic? So can I expect it to survive when I turn on epsilon? Not in this setting because that's singular, but after the rescaled setting. When I turn epsilon on here, then I get this equation, epsilon times y. That's a regular perturbation. We talked about that. So the stability checks out because the relevant Jacobian is just minus the identity. So so before perturbation, taking the x1 periodicity into account, your manifold is actually cylindrical. So this is a manifold of fixed points, and due to the x1 periodicity, it's a cylindrical manifold the x1 is in this direction, x2 is in that direction, and I kind of try to show the remaining transverse variables, which are the y in the remaining direction. So this is kind of just hand waving on my part, showing that we have the unperturbed fibers here, right? When you perturb them, then kind of they divert a little bit, but just order epsilon. And then we expect slow orbits. We know that there will be slow orbits on a nearby manifold. Well, the nearby manifold is guaranteed to exist because the critical manifold was normally hyperbolic. The nearby manifold will also be attracting because it normally hyperbolic. It inherits the stability type. So there exists a nearby slow manifold, right? And it's a graph over the original one. This was the original one. And therefore, I can just write down the rest, account for the deviation from that by adding a small epsilon times phi1x plus order epsilon squared. What this reflects is a smooth dependence of m epsilon on epsilon. Therefore, I can Taylor expand it up to order r. And the reason why we normally do this is not necessarily to get the manifold, but sort of the prize for all this, the objective is to obtain a reduced dynamics from the slow manifold, right? Because that is a very relevant asymptotic summary of what's going to happen in this problem, given that even though your phase space is either 4 or 6 dimensional, depending on the dimension on your problem, so your initial conditions will travel in that space. Ultimately, they do go to this slow manifold exponentially fast, and it's really fast, and they synchronize with orbits on there. So it is the classic example in which a reduced order model is very well arguable, and it will capture the asymptotic behavior, So how do I get the reduced order model? The recipe is that I take since the manifold is a graph over the x1 and x2 variables, I just look at the x equation and understand what happens in x. And if I don't want to get the y dynamics, then I'll just lift the x dynamics through this relationship, more accurately through this relationship, the Perturbation relationship, and then I get how y of t is slave to x of t, x of s. We are in the dummy variable, slow variable. So the x equation, when I turn on epsilon, is like this, and I have to restrict that to m epsilon. Now m epsilon, I only know approximately. So when I see y, I'm just going to plug in this expression. So by doing so, I have restricted the dynamics to the manifold. So generally speaking, this equation is not true for just an arbitrary trajectory of the system, but it's true on the target, on the reduced dynamics. So therefore, very quickly, exponentially, this will become relevant for any initial condition. Okay, and this also then brings in a question that I have not addressed before. You can say, I did. Let me actually write this out in original time. So in physical time, what you get in physical time is simply scale back to the t, so you drop the epsilon in front. So this will be ux plus epsilon times phi1 x plus order epsilon squared, right? So at leading order, you have this dynamics here, which is just the fluid dynamics, which makes a lot of sense, because at leading order, you want to see somehow that since the particles are small, then at leading order, they're really following the fluid trajectory, right? So this is a leading order. And to know that this is equal to the fluid particle dynamics. And I didn't go into calculating high order reduced order models in my general discussion, because I said if you get lucky, this already captures the behavior that you want, and you just look for structurally stable features of this, such as a limit cycle, torus, hyperbolic fixed point. And then you argue that for small enough epsilon, that's just a small perturbation, okay? Unfortunately, we're not getting lucky here. The reason is that we were setting out to explain this clustering phenomenon, which is a dissipative effect. Okay, this one is an incompressible two-dimensional velocity field. I don't even have to write it out. The authors of the paper have it. But everything I'm doing so far is in fact independent of the particular form of that wake velocity field. For any inertial particle motion, this is the leading order approximation. So it's completely universal for inertial particle dynamics. So just I take a look at it and I see, so in this case, this is a incompressible flow. So it doesn't explain what I set out to understand. So what I need to do in this case, so I actually need the high order terms in the reduced order model. Now, this is not always so. I mean, this is just specific to this particular problem where this, you can think of also this as a Hamiltonian system. Any two-dimensional incompressible fluid is Hamiltonian system. So these are, in general, they have no reason to be Hamiltonian. They might turn out like maybe extremely well, if they're Hamiltonian at odd order, I'm fine actually, because then what I'm doing is a Hamiltonian perturbation of Hamiltonian systems. So whatever is robust in the framework of Hamiltonian dynamics will survive. So for instance, if I have a center point here in a Hamiltonian system, and all these are Hamiltonian volume preserving, area preserving perturbations, then I'm fine, then it's robust, okay? If I have a homoclinic orbit, remember homoclinic orbits are robust when as level curves of a function. And if I'm adding Hamiltonian perturbations, then I have a Hamiltonian function, and as such, it will have robust homoclinic orbits. Closed orbits, same thing. The Hamiltonian to planar Hamiltonian system, important planar Hamiltonian system, those are robust, right? But I don't know that, so I need to actually go and see. I have no a priori reason to assume that these terms are also area preserving or volume preserving. So this is a good excuse for me now to go beyond the hand waving argument that I gave it and said, if you're lucky, this is enough, and see how you determine the higher order terms. So this is a general recipe, this procedure for them. So the question would be how to find the high order terms. What is the general procedure when you have a singular perturbation problem and you have the knowledge of the slow manifold and you go after details? Well, as always in invariant manifold calculations, the key is in the name. And that is not the fact that it's, well, the fact that it's a manifold, I'm using it all the time because I'm assuming I can do smooth calculus on it, right? Taylor expand, differentiate. So I'm assuming that, I'm using that. What I haven't used that is the invariance yet. So it's an invariant manifold. That's very important. So the manifold is invariant, then I can just plug in full trajectories and differentiate them, right? This would not be true for just any surface that I consider. So the invariance of the manifold is what's key. So the invariance of M epsilon tells me the following. I take the graph of M epsilon and I actually plug in full trajectories. So what was the graph? The graph was here. At this point, it's a geometric object. Okay, and it has nothing to do with, it's a static object. It becomes alive when I say, if I start on this, then I will have that satisfied for all times. So I can just put y of s here and x of s here and x of s there, and it remains true for any value of this x, right? So why don't I do that? I take the graph and then I say y prime, I don't yet say that, I just plug this in. I'm just copying this equation here with the trajectory plugged in. U of x of s plus phi 1 x of s. When we do this in practice, of course, I'm not going to write out always this dependence. I'm only writing this out for pedagogical reasons, because I just could have said, why don't I differentiate this with respect to S? But then you would not necessarily see why I'm doing that. I mean, there's no S dependence here, right? This is just a spatial point, right? So what really I'm trying to point out, that I'm exploiting that this is an invariant manifold, not just a set of points. It's an invariant manifold, so this holds for all S. That's what's behind. And then I do d by ds, okay? And then I actually drop the S dependence. So what do I get from this? I get y prime equals, and I get du, which is the Jacobian of u, and I get x prime plus epsilon times df phi1 x prime plus order epsilon squared. Now I'm using heavily all my knowledge of the equation and the fact that I have an invariant manifold. So for x prime, I actually have the reduced dynamics right here. Okay, so I can use that. So du is multiplied by epsilon times y, but that is epsilon times u plus epsilon phi1 plus order epsilon squared. There's actually a larger bracket at play here, right? So what I did, I just used the fact that whenever I'm on the manifold, and I'm on the manifold, this is really only valid on the manifold, I have the reduced dynamics of on the manifold in this form, right? And then I have other terms remaining here, namely these two. Again, if I'm lucky, then I just get away with leading order terms, which will be C at least order epsilon. And if I'm lucky, then not only luck, I mean, these calculations are all recursive perturbative calculations. So I go term order by order. So I don't forget that I have this here, but I don't have to be more specific. However, this looks like a first order term that I have to worry about, but only at first sight. Once I know that x prime is precisely this, therefore it starts with epsilon, right? So whatever I plug in here will be immediately order epsilon squared, okay? So I don't have to worry about it if at this order, it's gonna be, that will be put under the same umbrella as this term. And there are all order epsilon terms appearing here as well, in fact, already here. So those go in there, right? So I can just be even more specific. The only leading order term is du, the Jacobian of u applied to u. And everything else is order epsilon squared. Which seems like a pity, because then I lost any information about phi1 that I wanted to have. Okay, I'm doing this whole thing to get that phi1 in the reduced dynamics, but this is not the end of the story. When we use invariance, it's always there's always a duality. I first use it on the equation itself, and then I use the dynamics. And then I use it on the dynamics itself and use the equation. So what I mean by that I also have another way of writing, not that line, but this line. I have a more direct way of getting to u prime, namely the equation. The equation is always valid at any point. So what was the rescaled equation right here? This is always valid, but I'm gonna now evaluate it on the manifold. So I star it, this is star, okay? So my line of thinking now is that I wanna have another expression for y prime, and I use the equation, which is, it was here, what was that? U minus y, it's as simple as that. Ux minus y. But it has to be taken on the manifold itself, right? Which, just as this was taken on the manifold itself, otherwise it wouldn't be valid. So this has to be taken on the manifold M epsilon. That doesn't influence much what u of x is, but it does influence what y is, because y is enslaved to the x variable on the manifold, right, like that. So I write ux minus, and then I write ux, this was the first term, I'm writing this one out, and the second term is epsilon phi1. And then I order epsilon squared, right? So I have some luck here because these two seem to cancel out. So what I end up getting is at leading order minus epsilon times phi1 of x, and then everything else is order epsilon squared. So now I have two expressions for y prime on the manifold. On the one hand, I have this at leading order and then that at leading order. The only way both can hold is that they must be equal. So phi1 of x must be equal to a minus du x, so the Jacobian of x, multiplying, which is a matrix, multiplying the velocity itself. It's an interesting combination that arises. And I'm not going to go to higher order at this point, but this is the recipe. So now I have a phi1, okay? So I can go ahead and use that phi1 whenever phi1 arises, except that now I can go on and write these higher order terms explicitly out in both of the expressions. I will never use anything else, just these two alternative expressions for y prime. But I go recursively, as we did say for normal forms, or we did for center manifolds, always solve for unknown coefficients recursively, except that here I'm not solving for coefficients, I'm solving for whole functions. Okay, so as I solve it, the order epsilon, I got phi1, and I go to higher orders, phi1 will already be there, and derivative is phi1, I use phi1, and then I will get phi2 at that order, and so on. So it can be, I'll just say, this is recursive calculation, same idea. Gives phi2, phi3, and so on, if needed. So do I need it? Do I need to go higher? Well, it all depends. If this is also a divergence-free vector field, then either I have a general way of proving that it's divergence-free at all orders, therefore everything is Hamiltonian, or I have to keep looking for the next term, which is dissipated and no longer has the divergence area preserving nature. And then I have to add that in really to the whole vector field, and then I will get structurally stable objects out of it. Luckily, at this point, this is generally not divergence-free. U itself is, but if you start playing with this expression that the divergence-free nature disappears. It doesn't disappear. U is divergence-free, but it plays no role in. It doesn't make this one divergence-free. So it can have attractors. This one already. So we're in 2 dimensions. The model was 2 dimensional, so you can have an attracting fixed point that wouldn't quite explain the focusing. Let's see actually what the epsilon equals 0 velocity field is. The actual velocity field, which I'm not going to write out, it's in this paper, but I'm going to sketch it. It's very believable, the sketch you'll see in a second. Basically, you want to see nothing else but a von Karman vortex street in a frozen frame. Right? So you will believe me if I say, so this is first of all periodic. So you need to identify these two ends. And then so therefore it repeats itself endlessly. And it's something like this, that, one vortex would appear something like that, and then another one, something like that. And then periodically these streamlines are matched with each other. And then you will have one here, down here somewhere. So these are elliptic stagnation points, and they account for the vortices. They are more pulled away from each other more than I show, but so basically they are not aligned completely. I actually probably shouldn't draw them like that. So they're shifted. So, you know, one here, one there, one here, as you proceed. And in between, there are these just jet-like region. Just fill this up with streamlines. Maybe I draw just a couple like that. And let me get the arrow straight. So there are homoclinic orbits here, two hyperbolic stagnation points. So this goes out, so this must come in. Why do I see this connection? Because this is because I said these are not structurally stable. Well, this is a simple model with a symmetry. So these points are bound to have the same location and therefore the same Hamiltonian stream function value. That's why they're connected, right? But if this was a general Hamiltonian perturbation, then in fact you don't expect this heteroclinic connection to survive. You do want the homoclinic connections to survive. I talked about that before. You would also see these survive, and you would definitely see the hyperbolic fixed point survive if that's a Hamiltonian perturbation, but it isn't. So all bets are off. So when you turn on epsilon bigger than 0, and I don't remember if this analysis was done in the paper by hand. I think it was actually, if I'm not mistaken. People added you could also do this numerically, but people added the perturbation. And what they found was the following, that right in the middle, right somewhere here, the perturbation that they added actually created a periodic orbit, a limit cycle. So this point was the same as that, and that was actually an attracting limit cycle. So out of all those closed orbits, that extra term that they introduced, the phi1 term, created a limit cycle. And again, make sure you identify these two ends. That's why it's a limit cycle. If they didn't make this exactly periodic, then it wouldn't be a limit cycle, but there would be still an attracting line. And what happens is that general trajectories then, I mean, this is a non-hyperbolic fixed point, but I did this analysis in the first part of this course. It will still survive autonomous perturbations as a fixed point by the implicit function theorem as long as it has no zero eigenvalues, and it doesn't have any zero eigenvalues at linearization. So it's not guaranteed to survive as a center, but it's guaranteed to persist smoothly as a fixed point by the implicit function theorem. Again, the key to that is that the linearization has no zero eigenvalues there. And so there will be a nearby fixed point, but it actually turns into an unstable focus, and the trajectories leave that focus and they wrap onto this limit cycle. And actually, that's what happens with all these centers, that they become unstable foci, and all the solutions are getting wrapped onto them. There will be still hyperbolic fixed points here, the saddle types, and you can fit those into this picture as well. They, I didn't think about them. They're somewhere here, but I just want to emphasize that these von Karman vortices for heavy particles, this was heavy particles, so they would sink down. Interestingly, they spin them out. So maybe not so surprising. One way we have to I mean, I have this general intuition that if you have a center and I add dissipative effects, right, so to speak, then I will turn them into something dissipative so they become sinks. But in this case, not really. That's actually not a, it no longer preserves divergence, but it's actually an instability creating event to give these particles mass, because all of a sudden then the centrifugal force, so to speak, will spin them out, right? If they're massless, then they're happy just doing this without any feeling any force. But once they have a finite mass, then all of a sudden, if they do this, then there will be a centrifugal force and they're spinning out. So it makes sense. So in this case, the dissipation, which is this term here, right? Not really, I mean, the physics is interesting, right? Because the real dissipation here was in the equation to begin with. What we would actually physically consider dissipation is a damping type mechanism, which was in here in this equation, okay? That was damping. Yet at the level of fluid mechanics, damping doesn't, particle motion, it doesn't bring in dissipation because the flow is still incompressible. So Stokes drag or viscous force is generally, in terms of the Lagrangian fluid dynamics, they don't create dissipation. However, something that we would not expect to create dissipation is just the fact that you have a finite mass that ends up having a dissipative effect in this setting and can create attractors. So this is what happens there, and this is what you can either, this is not easy to, I think they did probably a version of the, if they did anything now, to be honest, I don't remember, but I now have a vague memory that they only got this numerically. So let's just say numerically. But there's a version of the Melnikov method, which we covered in the first part of the course, which is about the survival of, so the classic Melnikov method would be that what happens when you perturb a structure like this. Now here the perturbation is autonomous, so you will not get horseshoes, but what you can get is you will have a splitting for this. Now there's a version of the Melnikov method that asks what happens to periodic orbits like this. These are individually periodic. You could also ask the same about these periodic orbits. Now these periodic orbits all turn into unstable spirals, and most of these guys also lose their periodic nature, but there will be one surviving, and that will be the zero of an appropriate subharmonic Melnikov function. That's in principle computable for perturbations of Hamiltonian systems, but I think that in this case, they probably didn't do that because the orbits are fairly complicated. So I think they were better off doing this numerically. One thing I wanted to note about the reduced order model, I think, did I write this out in, yeah. So this is not the only use of these reduced order models on slow manifolds, but the reduced order model on the slow dynamics, so reduced order dynamics is also useful in general for what we call source inversion. And source inversion would be the following problem: that you have some substance in the air or water, it's coming from somewhere, and you would like to trace its origin. And at some point years ago, for sad reasons, this was a very popular research subject in the US because everybody was worried about anthrax attacks and biological weapons. And maybe we should still be being worried about that, but it's not so much on the table as it was then. So there was a lot of funding and going into just setting up sensors in cities, and the sensor would go off and detect some chemical substance, and that's important to know. But equally important is, where is it coming from? Where's the source? And suppose you have a model for the wind field in the city, and you have some understanding of the finite size anthrax particles or whatever substance that is. Can you, given your running model of the wind field in the city, and given the fact that you have measured the presence of these molecules at various locations, can you invert that and see where they converge, because then you would be able to zoom in where, say, a dirty bomb went off, which is not necessarily something that you immediately know. Okay, so that was one application that I was a bit more familiar with, but generally speaking, source inversion in problems with two timescales is a challenge. And the reason, and yet source inversion typically involves problems with two timescales, because you're after the backward fate of small particles to begin with, right? So that immediately brings in this duality of timescales. So inherently, it's a hard problem. And why is it a hard problem? It's a hard problem because of this, that if I now complete the full picture in a two timescale problem like this, and suppose you, just to be specific, although what I'm saying is not specific to the equation that we're studying currently, not to this particular von Karman vortex street, but generally speaking, you have all these trajectories coming into the slow manifold. In fact, some of them, might come in and then takes a spin around one of those vortices and comes here, and then maybe the other one goes there directly. Maybe the third one comes in here, right? And maybe, how's the spinning here? It would get close and then do a spin like that. And so all sorts of outcomes are possible. But look at the shapes of these trajectories. Now I say, okay, so I'm somewhere here. I'm never exactly on the slow manifold, because me being exactly on the slow manifold in this 4 or 6 dimensional phase space has probability 0, right? This is a 2 or 3 dimensional manifold, not even codimension 1. But even if it was codimension 1, what's the likelihood of me being on it for general inertial conditions? That's 0. So what will happen, though, is that I'm going to be extremely close to it. Okay. So suppose you want to find the source of your contamination, your particular trajectory, because it very quickly came here, it's somewhere doing its thing, and then you say, I have a model for what happened here. Can I just take that initial condition and invert it? And since you're not on the slow manifold, you're going to be facing the following problem, that no matter where you came from, you came in pretty steeply. So when you invert that, at some point, you're facing this incredible exponential instability. And as a result of that, whatever solver you have is going to go through the roof and blow up. It's unavoidable, because you do have exponential growth. So what that means is that suppose you came from somewhere and then came down here, somewhere here, and along that course, your solver will do this, and you will never be able to say that where you started from. So that's an inherent problem with source inversion problems. So the challenge is it's this exponential instability in backward time. And like I said, it points way beyond beneath this problem. In fact, it occurs at the level of the PDE2. If you're using the advection diffusion equation, which is your usual transport equation. So this is actually even I'll just note that here at the level of PD simulations of advection diffusion. This has just occurred to me. This is just a remark. So what would be an advection diffusion equation? So for some sort of scalar, let's not use U because let's just say CT, okay? And then you take the gradient of C dot V. This is for incompressible flows. So this is just the material derivative of C with respect to T. If I write 0, this equals 0, that's just a conservation law. That means that the scalar, so this is a scalar field. This is, say, just a concentration field of the contamination. If I say this is equal to 0, then it means that it's conserved among trajectories. But the advection diffusion model is that you just, with some diffusivity, you throw in the Laplacian of this. And that helps you in forward time a lot, because the Laplacian operator is a very nice operator. If you had any bump in your initial condition, it's gonna make it arbitrarily smooth, over arbitrary short time intervals, because Laplacian has this smoothing property, and that's exploited a lot of times. But what works for you in forward time, it works against you in backward time. You may have heard this difficulty with the heat equation. It's very hard. So basically, yield pose is very hard to find the initial condition because of this exponential loss of smoothness in backward time, right? So again, you had some rough initial heat distribution, temperature distribution, right? And forward time, in a second, it's going to be smooth, but try to do that in backward time, right? Precisely because it tries to recover those going from smooth to non-smooth. So the same thing happened with there. So that's also a separate area, that if you don't try to model substances as particles, but you try to model them as for what they are, concentration fields, you face the same thing there. So this is ill-posed in backward time. So the same happens here at the level of an ODE, that it becomes very hard to solve. Basically, any solver will blow up for you. However, if you say, you know what, I don't actually intend to recover, if this was my trajectory, let me actually be a bit more specific, one particular trajectory. So maybe the trajectory, came in here, and then it did that. And your blow up will already start happening somewhere here, and you will see this. And you say, you know what, I actually don't care so much what my initial velocity was, because that's not my interest. I show some initial directions here. So this was the y direction, which is the velocities, and this was x1 and x2. So these are the velocities, and I'm not so much interested in getting the exact velocity right for the initial condition, which started from somewhere here. So this was t equals 0. But I'm content with actually perhaps trying to find the initial location of the release. And in applications, as the name already says it, I'm just interested in the source location. So this is the type of information that I'd love to have, okay? And since the fibers after perturbation are very close to being straight for epsilon equals 0, actually, this initial condition was very close to a fiber that was absolutely straight through that point. How do I draw this? So this will be I think I messed things up a bit. So let me clear this up a bit better, because there are two different things here. One is the actual exact location, which would be, say, here. So this is the release location. Just location, no velocity. Okay. And then the other question is that I started talking about is the existence of these fibers here, which are pretty close to that. So it will run into a nearby base point, not in. So this is the fiber base point, stable fiber base point for the initial condition. So the initial condition started on this fiber. So it is doomed then to follow the orbit that goes through that fiber. So if I figure out what that orbit is, That's going to be a good approximation to this actual orbit. So this is the orbit, reduced orbit. Through this base point. Okay. So the idea is the following, that instead of trying to do the impossible and do this, why don't I just do this? That I actually project this trajectory down. So in fact, I take just the initial condition of its projection onto the manifold. So I kill off all the components that it had of the manifold. Too many colors. So just project it down, okay? And I start going backwards. And then I will be close after I to that base point, the actual location and the base point, both of them, right? And I can do that without any problem, because on the slow manifold, I can invert the slow flow without ever experiencing the instability. I have completely eliminated that. So this is the reverse simulation of projection on the slow manifold. And you say, well, I still have to be careful. No, I don't have to be careful anymore, because on the slow manifold, I simply don't have to, I won't see the instability at all. So when I have a reduced order model, where's my reduced order model? The reduced order model, did I write it out? Well, someplace. So let me write it out again. The reduced order model is just x dot in real time equals ux plus epsilon times dux plus order epsilon squared. All these, so this is the reduced order model. All these terms are functions of x only. So this is a self-contained simulation that I can run in backward time without ever facing any instability from the y direction. So I can just go on and do this, right? So I will lose all the velocity information. So I will not have this, but I will, if I know how much time has passed from that release, okay, then I can just say, all right, so it's been about, what, 30 minutes. Then instead of trying to do the impossible, I just work with the projection and I go back. So this idea, I can show you, if all goes well, on a slightly more elaborate model of the same flow. I think this is it. This was a movie done, a long time ago by Themis Sapsis, who's now a professor at MIT, but he was a student of mine at the time at MIT, and we were very enthusiastic to try out these ideas. And what you see here is the two directions. So they are called X and Y here. I don't know, can I point here? Not easily, maybe with my arrow. But you don't see my arrow. I'm not sure how to point. Anyway, X and Y are the two coordinates. They would be X1 and X2. The vertical direction is the velocity norm squared. And you see a cylinder symbolically in the middle. I mean, the cylinder expands in the velocity direction. So you have to take that with a grain of salt, just for visualization purposes, just to give you an idea. And you see this bumpy floor there. The bumpy floor is the slow manifold. So what Themis has done, he took the norm of the velocity field pointwise, okay? Because remember, the leading order slow manifold is just y equals u of x, and he's showing that right here, okay? And you see more bumps than the vortex street because it's a slightly more involved model, but it's nevertheless the same type of model. And what you will see here is that on the left, you see that little cloud. And from the cloud, there will be trajectories coming towards the slow manifold. And we will be also doing the following, projecting them down to the slow manifold and just simulate their projection, okay? And then at some point, we will stop the whole simulation and try to do the impossible for the red trajectories with very careful numerical integration to trace them simply back in the same deterministic ODE. There's no diffusion here or anything. You're just trying to run the exact same trajectory backwards, with a very highly accurate trajectory solver. Do that, and also just try to run the projection on the slow manifold, which is not a big deal. You only run the reduced order model. So let's see what happens. This is in forward time. See, they're really moving together as they should. And this really shows that the fibers are almost straight, because the trajectories are pretty much doing whatever the base point of the fiber is doing, right? So that's why it really shows that the reduced order model is working very nicely, capturing essentially the shadows of the trajectories at a fraction of the cost, because you're running a two-dimensional system as opposed to a four-dimensional ODE. But you could say in forward time, you know what, I don't mind running a four-dimensional ODE. It's not a big challenge, and you're right. And there are bumps on this slow critical or slow manifold. The two are close to each other because that's just the velocity, what the velocity field does. It's not a straight. So they're hopping around. Okay, at some point we stop the simulation. Now let's run backwards. Same points. Everybody's running backwards. And the red ones were the ones off the slow manifold. This should be the exact same trajectory. See what happens. The solver is just giving up. And those, you get an NAN on those. And look what happens to their projection. Nicely goes back to the same point. So what we did, you know, when in fact the backward runs are just projecting the red ones at that point and running the projection backwards and running the red ones backwards. And you'd say, hey, it's a reversible procedure, right? Integrate forward time, integrate backward time, same solver. No, it's not. The solver really has a hard time in backward time. And it's not a low order solver. It was a pretty advanced solver. So that's the challenge of source inversion, and you see why that is facilitated, why this challenge can be overcome very efficiently by using the reduced order model.
Professor?
Yeah.
From a physical point of view, I've got a quite hard time imagining that if the velocity blows up of the trajectories, would send...
No, it doesn't. It's only the solver. That, I mean, there's an exponential instability, right? That you're trying to simulate in backward time.
Okay, now it makes sense then. Yes.
Yeah. Just like the heat equation, right? That it did start from a realistic, whatever that initial condition was, you imposed it and you try to recover it. And then you say, hey, I'm just looking for where I know that this beam has this temperature distribution right now. I know it started from a reasonable one, at least bounded one. Now, why am I not getting that back? Why is that? And this is the reason, right? The same sort of development of small scales, that instabilities that are unsurmountable, essentially.
Thank you.
Okay, that's a good point. It's not an unphysical thing. It's an unmanageable thing numerically. Anything else? So this is not the end of the story about this class of problems, because there's some interesting stuff also still related to initial particles. If you want a more detailed model, and you can take this to the extremes, which I'm not going to do, you can start including memory terms and everything. But let's just take one step further. So this is sort of the end of this story. So the more general model for what I'm going to now look at is neutrally buoyant initial particles. So it's not going to be substantially more complicated, just one more term. And neutrally buoyant just means that the density of the particle is the same as the density of the fluid. So you put it, it's basically, it would be floating there. Okay. And a lot of the times, these are the particles you would use in PIV, particle image velocimetry, because you don't want your particles to be, you don't want the flow region to be depleted. You don't want the particles to be sinking to the domain bottom, or you don't want them to go upwards, right? But you want them basically to be floating. So neutrally buoyant is very important. So anything that kind of floats around in the air or in water. So that model is just it's ever more slightly more involved, but also it will be now more general in one other way, which I'll say. So this is the only term that I'm adding here. So it also turns out to matter what the material derivative of the velocity field is, okay? And this is the next term, which is a term that I have neglected so far. And the neutral buoyancy gives this particular coefficient for that term. So I don't have any other constant there, but otherwise it's very similar. And this is epsilon is still the small, which I always forget, it's I think 3 times the Stokes number, because 1 over epsilon is the Stokes number, right? You have some sort of heavy drag here, and then the 1 over epsilon becomes epsilon when you had 1 over epsilon here, which was your mu. That's what the Stokes number came in, and we multiplied that out, you get epsilon. So it's this equation, and this is for suspensions. And suspensions are the neutrally buoyant particles. So it's just yet another name for them. So density equals the fluid density. So again, it's the same type of formulation, except that now I also allow, for something I didn't do before, is that I allow this to be unsteady, this velocity field. And for some reason that wasn't handled in the literature for the longest time. And then again, this was at the time when Themis was a PhD student. So I think this was actually the reason why we started working out geometric singular perturbation theory for non-autonomous systems. So there's a reference that I think does that first. We had several papers on this. This happens to be one, I think, from 2008, and it came out in Physica D, which at the time was the leading journal for nonlinear dynamics. It's still pretty well known right now, but by now there are also other journals. So it's more this, what was new here is this time dependence. So all the references, just think back to this problem. They didn't deal with this in the lab frame. They had to move to a moving frame in which the equation was autonomous. And they didn't say how this extends to non-autonomous systems, because all the papers written by Fenichel on the subject were for autonomous systems, right? And in the derivation, the autonomous nature was important. So can you still come up with a similar formulation for this? So the singular perturbation formulation, is that possible? Why it's not obvious is the following, that any kind of rescaling of time that we do in dynamical systems works very well in general, as long as the system is autonomous. But when you start rescaling time, I'm getting all these notices, sorry, then you might fix something in your equation, but then remember, then you would have to actually act on this now explicit occurrence of time on the right-hand side as well. And that is usually then very often messes up your whole construction. Whereas when you have an autonomous system and you tinker with the time, with the trajectory-dependent rescalings, it doesn't matter in the end, but because there's no explicit dependence on time. But the minute you have it in non-autonomous systems, then usually it backfires unless you do it, it's in a setting in which you get away with it. So here's the idea that actually, I think I was actually teaching this class, and as I was preparing for one of the classes, and I was going to say this only this only exists for autonomous systems, and all of a sudden before the class I said, oh, wait a second, it doesn't have to be restricted to autonomous systems. Why? Because as I was working out the notes, I just made the following observations that let's just introduce a very similar rescaling of time as before, but I have to favor now an initial time t naught, I implicitly favored 0 so far when I did the fast time introduction. So I introduced the fast time now through this relationship. So T naught is some initial time of interest. And then the only trick that you need is that the observation is that if I now differentiate this variable t with respect to tau, then that's just epsilon. Okay, so now I do an extended singular perturbation formulation. So not only do I write out the x equations, which would be x prime equals epsilon y, remember, in this formulation. And that doesn't change because the fact that I added this t naught here does not change the chain rule. When I differentiate with respect to time versus tau, this constant is not going to care about that. Okay, this will just help me focus on different parts of the non-autonomous evolution. But then I add one more slow variable, which is just t itself. And the fast variables are just the same as before. But it's okay for me now to write uxt. See, that's the thing. Because all of a sudden, this is my new slow variable here. So if I just had this one and that one, then this t just wouldn't jive well with Fenichel's theory. I would have to also, plug this in there. It wouldn't be clear what to do with that. But t is now a slow variable, so I can just leave it at that. And the only difference is that I have the minus y here again, and plus I have plus epsilon times du xt dt. That's it. So this is now slow fast form. And this is suitable for singular perturbation theory. And for some reason, I mean, I don't know why, prior to 2008, I mean, this is a trivial observation. I don't want to exaggerate it. Like I said, I was preparing for a class and I said, why don't we do this? But for some reason, before that, there were absolutely no geometric singular perturbation theory papers on non-autonomous systems. And people were actually avoiding, passing to moving frames and everything. And it just works the same way. You just do this trick. Right? There's no free lunch. So what's the no free lunch? What is the price that you're paying? The price you're paying is that t, you can't just immediately, your conclusions will be valid on some finite time interval for any given epsilon when you talk about uniformity, because you will be running out of time, so to speak. The critical manifold that you may be getting, generally speaking, from this M naught, which is filled with fixed points, you even freeze the time. So time is in this direction, t. So this is t, and this is x, and this is y. So remember, M naught had to be compact for Fenichel theory to work. So t must be restricted to a finite time interval in each of these arguments. So when you say, M naught exists, I will find a small enough epsilon that M naught exists, I can make such a statement, but only for any compact piece of M naught. I can't make that statement for all times. And when I do this analysis for longer times, therefore, I have to reduce epsilon. So it really then has to. So if epsilon is really a finite quantity of interest for you, then this will not work for all times. It will work for long times, but not for all times. But if you're lucky during those times, you've already captured what you want. This is the only thing you have to be aware of, because it has to be compact. But time is nicely frozen, right? When and only the dummy time tau runs. But when you turn things on, then you will also start having slow evolution in the time direction as well, right? So when I calculate then M epsilon, what is changed? So again, this is one change, that all of a sudden the dimensionality of M naught is larger. So in a two-dimensional problem, the dimension of the critical manifold all of a sudden is 3 if the particle, if X was two-dimensional. Okay, so that's one difference. And the other difference is this term here, which I didn't have before. Other than that, it's the same calculation. So the epsilon equals 0 analysis that gives me the critical manifold even gives me the same critical manifold, because for epsilon equals 0, this term is out. So M epsilon is again characterized by this graph, but I have to write it's now the set of X, T, and Y. So this is taken from R2 cross R cross. And I forgot to restrict it to some compact set. So this is taken from some, say, U, which is part of R2, and then cross T0, T1 cross R squared. And U is taken from R2 when it's compact. That's the spatial domain. But other than that, the actual formula is Y equals U of XT. So this slow manifold, critical manifold, will be breathing in time. It's not going to be the same constant in time, so as which it was before, but it will be once I turn things on. When I turn things on and went back to the original scaling, in this problem, it was the same manifold. And remember the movie that Themis made, it was pretty much the same bumps. That's not going to be the case here. The manifold will be breathing in time, M epsilon. It's a time-dependent slow manifold. And in fact, it can be pretty complicated. What I know is that the same stability analysis works. It will always be at, well, as long as epsilon is small, right? Because now I have some competition. But not just that, but when the analysis that we did for the stability of M epsilon involved the Y derivative of this equation, and that's always minus identity. But that's a local argument always from linearization. When things can start changing, ultimately that locally that's what matters. But when I do an infinitesimal calculation, but as this term also becomes large and starts shifting the manifold to some finite distance from what it was, then also that comes into play, as we'll see later. So, and as far as the the leading order stability for epsilon equals 0, I mean epsilon is small is the range in which this whole argument works. So for when epsilon is large, all bets are off. But for small epsilon, this works. I have a time dependent but still attracting slow manifold. And what is it exactly? So when you go through this calculation, very similarly, you do Y prime, but I'll just write this out because there's a minor difference and I want you to be aware of that. And I made a mistake here because I forgot about the high order terms. This is the leading order term, but then you have plus epsilon times phi 1 of x and t plus order epsilon squared. Okay, so again, what I do now is Y prime one way, which means that I'll be differentiating this relationship with respect to the dummy variable s, and mind you, t now depends on that s as well, and x depends on that s as well. So when I do the differentiation, interestingly enough, I have to account for the fact that t depends on the dummy variable. Well, it's not s, sorry, it's tau. Okay, where was it? It's here. So tau. So when I do the d by d tau, d by d tau of what? Let's so I already had a star, so this is double star. So when I do that, I get y prime, and then I get du, and from and I remember that from x prime, I immediately write what x prime was. That hasn't changed. Remember, x prime is just epsilon times y, which is right here, but y at leading order is u. So this will give me epsilon u plus order epsilon squared, and that hasn't changed. The new element now is that I also have to hit this argument here with the tau differentiation. So I need to take formally the partial of u with respect to t, and now I have to differentiate t with respect to tau, and that is right here. So that's just epsilon. That's the right-hand side of this slow equation, okay? So that's one difference. And then I go on, and as far as the second term is considered, so this is epsilon phi, I will take the d phi 1. And now I have to do x prime, but x prime is epsilon times y, which is here. So that is again epsilon times u plus order x squared. So when the dust settles, I have at order epsilon, I have duu again from this term here. But I have a new player here, this one. So that's just dtu plus order epsilon squared. And lo and behold, this is now something that I recognize as the material derivative of u. But material derivative in the original fluids setting. So it's not in the inertial particle setting, right? Because if I took this material derivative with respect to inertial particles, sorry, then I would have this term for sure. And then I would do grad u times the speed of the particle. But no, this expression is not that. This is the speed of the fluid. So I do mean that this is a material derivative with respect to the fluid particles. So du dt notation, this is the material derivative with respect to the fluid particles. Okay, but luckily that's exactly what I had here. So that's how I mean it there. So basically evaluate the material derivative for fluids, and therefore, and then you will get a term like this, because your chain rule will give you u as opposed to x dot, which is v. And that's the term that comes in the modeling of the phenomenon as well. Okay, so that's good. So this is on the one hand, and on the other hand, when I do and this is triple star, then triple star gives me, I use the equation itself, y prime, and I can read it off, equals u minus y. I'll just repeat it here, plus epsilon du dt, okay? And I need to take that on the manifold itself, as I had to do that here as well. So that's u minus, now y is just what it was, u plus epsilon times phi 1. Both u and phi 1 now depend on x and t, plus order epsilon squared. But now I have this term here, which is plus epsilon times du dt. So all in all, the u's are again canceling out these two. And what I end up getting is minus epsilon times phi1, but it's at the same order. I have plus epsilon times du dt, plus I have the order epsilon squared terms, which is an unfortunate development from the point of view of analysis for the following reason. I have to equate now this y prime and that y prime. So this will be equal to that, which immediately gives me what? This is only possible if phi1 is 0. Identically. So it's one of those situations when I went one order higher, and I had to go one order higher because, again, the flow was incompressible. So this is Hamiltonian system when it's two-dimensional. So when I add then high order terms, who knows what's going to happen? So I added the first high order term, and you know what? It vanished. What would be the general strategy? I go for the second high order term, the third. Now, we did this in the paper, but I think this was known to begin with, that in fact, up to any order, this is 0. So what's the conclusion? The conclusion is that on m epsilon, the reduced dynamics is identically equal to the fluid dynamics. X dot equals u of xt. So that's a nice result in general, that if you have, on the one hand, it's reassuring. It means that if you do PIV experiments in which the little particles are neutrally buoyant, then if they are really neutrally buoyant and they are small, so that this analysis is true, then they will exponentially fast synchronize with the slow manifold. And on the slow manifold, they will do exactly what the fluid trajectories do. So small neutrally buoyant particles, when you track them with a particle image velocimetry, will give you a true representation of the fluid motion if they are small enough. That's very important to know. So the smallness was important because this whole theory only works in that limit, right? So that's a good thing. You will have a very short initial, when you release them, you will have a very short initial period of synchronization. For instance, you release them with 0 velocity, they will need time to pick up the fluid velocity, but they will get exponentially close. Now, will they ever exactly synchronize with the fluid trajectory? No, but they will get exponentially close. You will not see the difference. So the conclusion is that neutrally buoyant particles synchronize with fluid particles. So I have to say small enough, right? So that exponentially fast. So that's a good thing. And so that's what we should be seeing. And then I don't know when exactly when we, and this was kind of in the air, right? An experimentalist would believe in this anyway, right? I mean, they would say, sure enough, that's what we're doing. We know it from experiments. But I think as I was reviewing the literature, I found a segment of the physics literature that just showed that this is not true based on numerical simulations. And that really puzzled us. So why is it? I mean, this is what the experimentalists are telling us, that if the inertial particle is buoyant and neutrally buoyant and small enough, it will synchronize, right, with the fluid particles. That's what we're getting from this rigorous analysis. There's no difference. There's no higher. We did the up to any order you can do it. And yet there are papers that report what is a scattering phenomenon, which means that they do simulations on this equation, and yet they see that the neutrally buoyant particles, from time to time, they deviate from the fluid particles. And that that just blew my mind. So why is that possible? How is that possible? So yet, what's the term? I think that scattering, right? From fluid particles is reported in literature. And that preceded our work. So then, so I guess we started looking at those papers that reported it. And one thing we noticed, luckily, first sign of relief, that epsilon in those simulations was not particularly small. It was on the smallish side, but it was, you know, not infinitesimally small. So maybe that's the reason. Even then, I mean, there's no indication from this analysis by itself what would go wrong, but then we decided to take a look at that. So to understand that, the question is why. And there were actually some analysis in the paper that I cited. We referenced all these papers, and there was some formal analysis done by physicists why that should be the case, right? Not mathematical analysis. We wanted to understand from our perspective, from invariant manifolds and Soule manifolds and whatnot, why that happens. So one thing is to do, and this way of rewriting the equations we learned from these papers. It didn't occur to me to be able to do this, but it's basically the following. Let's go back to this funny issue with the material derivative, which is a material derivative with respect to the fluid, but not with respect to the actual trajectories of this system. And let's actually try to correct that. Let's try to write the right thing. So the equations were like this: V dot, originally, I think I'll just repeat the equations, V dot minus ut and minus duu, but now without the rescaling. This is the du dt term, but there's no epsilon there. So that epsilon actually came from 1 over epsilon, which was in turn mu. So I just put together put it back together to the original form in which mu is no longer assumed large. You know, epsilon equals small meant mu was large. So this would be the general form of the equation, inertial particle equation. If you say, well, the particles are okay, they're going to be small, so mu is going to be sizable, but I'm not going to say that it's as big as that 1 over epsilon would be almost like infinity, right? Just some sort of decent large, but not incredibly large, right? So, but to relate it to what we had before, mu is 1 over epsilon. This is how the epsilon entered the whole picture. So you start from this and let's correct this funny business. So what I'm talking about the evolution of V. So wouldn't it be nice to have the true, honest material derivative with respect to the evolution of the inertial particles, which would be the following. It would be grad u times x dot, but now x is the inertial particle position, so x dot is v then. Well, that would be nice to have, but that's not what I have there. So I have to correct for that. So how do I correct for that? Well, in order for me to be able to write that, I had to add delta uv to the equation, and I had to ignore the minus delta uu. Okay, so if I put that on, I can account for that by taking this and putting it on the other side, and also then subtracting what I have just, by also adding this term that I have added here. So this is plus, and except that I know something was not adding up. This is a plus because I have included this parenthesis here, right? Okay, so I'm actually subtracting this term, so I have to subtract it on the right-hand side as well. So the two equations are equivalent if I write delta U times U, which I'm getting from here, and I put it on the other side, and I have to subtract V. And this is something, it's kind of just a neat observation we did learn from the existing literature, that the physicists who were working on this figured this out. Okay, so when you have it like that, then this is really then the du dt with respect to inertial particle motion. So all of a sudden, from the point of view of your actual dynamics, so then it's okay to rewrite this as d by dt v minus u, because all I did is just, I'm applying the d by dt to the trajectory motion, its velocity, and then this is then, you know, that's just x dot, which is now the inertial particle motion. And on the right-hand side, I can pull out u minus v, but I'd like to have v minus u. So I write minus, and then what order did I, grad u plus mu times identity applied to v minus u. And you might see then why this was a very insightful thing, whoever noticed that first. All of a sudden, if I call this, say, z, we called it z, then this is actually a linear equation for that z. That's the deviation from of the inertial particle velocity from the fluid velocity. So I have z dot equals minus grad u. Well, it's a funny, it's not really a linear, it's a linear equation for z, but generally speaking, it's a nonlinear equation because this does depend on x, and x has its own equation. X dot is v, but I have introduced z for that variable. So x dot is z plus uxt. So it's not really a linear equation, but at least the first equation is linear in z. That's the right thing to say. And that actually shows you something else that was not immediately clear from, no, we did have that in the paper for epsilon small enough because we also calculated the shape of the manifold up to any order. Well, look at this equation. Z equals 0 is invariant. So it means that when u is equal to v, which is the critical manifold, then up to any order, the critical manifold is flat and remains flat even after perturbation. So the slow manifold is also flat up to any order, which we had for small epsilon, but not in general. So I just, I'll finish this up tomorrow because something really interesting will come out of this and explains the scattering that people have noted. There's no contradiction because I'm no longer assuming that epsilon is infinitesimally small. There will be a finite epsilon here. And maybe it's small, but it's not infinitesimal. Any questions? No questions. Okay, then see you tomorrow.